going through Level 2 Physics 2022 Electricity and Electromagnetism examination paper. So let's start with question 1. This is on electric fields. So two parallel plates are set 2.2 millimeters apart with 15 volts between them. So we've got to show that the electric field strength is this number. Now there's a catch here. The 2.2 millimeters needs to be converted to meters. So that's what I've done. Electric field strength is V over D. This is your voltage and that's your distance. And it's times 10 to the power of negative 3. Why? To convert the millimeters to meters. And for sure that question, write the formula, do the substitution, write the unrounded value, and then here's the answer that you need. And that's what an achieved. Now, an electron at rest is released from the negative plate and accelerates towards the positive plate. Calculate the maximum speed of the electron when it reaches the positive plate. So in this one, the electrical potential energy lost by the electron is gained as kinetic energy. So these two values are the same. So the electrical potential energy is equal to EQD, where E is the electric field strength. I use the unrounded value here. So you might get slightly different answers if you use the rounded one. So that's the electric field strength. This is the charge on the electron. This number is given on your resource sheet. That is your distance. Multiply the 3, you get the electrical potential energy. Now this amount is equal to the kinetic energy, which is half mv squared. This is half. The mass of the electron is also given on your resource sheet. So I got this number from there, times v squared equals that energy. And then you get v squared and you go square root, you get the answer, and that's worth a merit. Now, a student states that increasing the distance between the plates while keeping the voltage the same will mean that an electron released from rest at the negative plate is accelerating over a longer distance and will therefore reach a higher speed than in part B when it reaches the positive plate. And we've got to use physics principle to say why this is not correct. Now this is incorrect because when the distance between the plates is increased and the voltage is the same, the electric field strength decreases because E is V over D. So if D increases, that decreases. When the electric field strength decreases, the electric potential energy lost by the electrons remains the same. Why? Because if that's less, that's increased. So the electric potential energy is the same, so it will reach with the same speed as it accelerates over a greater distance but with less force. Okay, then state one thing that could be done to increase the maximum speed. One thing that can be done is increase the voltage across the plates so that the electric field strength increases. D. The diagram below shows the electric field strength between a set of parallel plates d meters apart with V volts between them. Now the distance between the plates is doubled and the voltage is halved. Okay, so they're further apart and there's less voltage. Less means it's halved. State what happens to the strength of the electric field and your answer should include a number. So the electric field strength decreases 4 times because electric field strength is V over D. So what's happened to V? V has become half, so you divide that by 2. What's happened to D? It's become twice. So you get 2 times 2 is 4. So the electric field strength becomes quarter V over D. So 1/4 V over D. Somehow that got rubbed off. Okay, there we go. So that's worth a merit. Now, using the same scale, draw in the field lines on the diagram below to show the new electric field strength. So because it's become quarter, and initially there were 12 field lines. So I counted the number of these lines. There were 12 of them, and a quarter of 12 is 4. 4 divided by 12 is 3. So you already got 2, just needed one more. Okay, next question's on circuits. A student finds some car headlamps that are labeled 12 volts, 55 watts. Show that the resistance is this. So this is a 2-step calculation because I first got the current using P is equal to V times I, or I is P over V. This is our power. That's a voltage. Here's the current. And then I used Ohm's law. V is I times R, or R is V over I. And that's your voltage, that's my current. And then I wrote the unrounded answer for resistance, and here's the rounded answer. Okay, the student connects two of these headlamps labeled A and B and another lamp C, which is used to light up the number plate in the circuit below. The resistance of lamp C is 1.22 ohms, so that's different from the other ones. Calculate the total resistance of the circuit. So in the circuit, C is in series, those two are in parallel, so it's a combination of both the formulae. So that's your series, that's your parallel, and you do the 1 over, and then you get the 1.31, which is the sum of those in parallel, and you add it to the series and you get 2.53, and that's your merit. The student connects a radio with resistance R to the circuit, so the radio is here, it's in series with B. Okay, use physics principles to describe the effect adding the radio would have on the brightness of lamp A. Assume the radio and lamps are all operating. Start by describing what effect adding the radio would have on the circuit resistance. So adding a radio here will mean the resistance of that branch is increased. So the total resistance of the parallel has increased, and therefore the total resistance of this whole thing would have increased. So if the resistance increases, then the current drawn from the circuit will decrease. So if it's a smaller current passing through C, the voltage drop across C will be less. So there's less voltage here. So the voltage that this parallel part gets is 12 minus a smaller voltage. So the voltage across A will be bigger. So it's going to become brighter. Okay, because the brightness of the lamp depends on the power output, and power is V times I. So that's how you get brighter lamp. Then give at least 3 reasons why the circuit in part C would not be a good way to connect the 12-volt headlamps in a car. So there's lots of reasons. Connecting a radio in series with the headlamp will mean that the voltage across lamp B will decrease. So lamp A and B will not be the same brightness. Lamp B will always be dimmer than lamp A. Then the voltage across the headlamps will always be less than 12 volts, because some voltage is always used by lamp C, so it will never be at its full brightness. And the other thing is, if lamp C blows, then nothing will work because lamp C is in series. And also for lamp B to work, the radio has to be on because it's in series with the lamp. So you don't need all these reasons, you just need 3 of them. Moving on to question 3, which is the electromagnetism part. Magnetic fields, and you're given some data here. A wire is pushed through a magnetic field at a constant speed of 2.70 meters per second. You got the length, you got the magnetic field strength, which is in millitesla, and you got the width of the magnetic field, which is in centimeters. So just remember, anything in centimeters needs to be converted to meters. Okay, so what is the voltage induced across the wire? So the voltage induced is BVL, the first one is mark the positive end of the wire. So here's your positive, there's your negative. This is fields coming out of the page, and when you use your hand rules, you get that as positive because that's where your thumb points. Okay, so induced voltage, V equals BVL. So this is my B, so converted the millitesla to Tesla, and this is your voltage, and there's your length from centimeters to meters, and you get your voltage induced. And that was an excellence, okay? That's an easy excellence. The wire is now stationary and connected to a circuit that contains a 3.40 ohm resistor and a 12-volt battery. So now it's no longer electromagnetic induction, but it's looking at the force. Calculate the magnetic force on the wire. F equals BIL. So you've got to get the I, which is equal to V over R. You get 3.53. I just kind of did it in one step, but you can do it separately. So this is the B. That's how you get your I, and there's your L, and you get your force. State the direction of the magnetic force on the wire. Again, when you use your hand rules, you will get the force is to the left. Then, an electron cutting the magnetic field experiences a force that makes it follow a circular path. So you need to draw whether it's clockwise or anti-clockwise. Here again, when you use your hand rule, you get your anti-clockwise circle. So that's how you mark the direction. Now, use physics principles to explain why there is a force on the electron as it cuts the magnetic field. Now, this might kind of put people off because thinking, oh, we were just told that there is a force and it's equal to BQV, but why is there a force is this question. So, here's the answer. Whenever you have charges that are moving, these moving charges constitutes an electric current if it's contained in a wire, and you know that any current carrying wire has a magnetic field around them. Similarly, even if they're not contained in a wire, moving charges will have a magnetic field around them. So what happens is now you have your moving electron with a magnetic field around it. It's moving into another magnetic field, so there's two magnetic fields over there. And they kind of combine together, and this causes a centripetal force on the electron, causing it to move in an anti-clockwise direction towards the weaker field, okay, because fields kind of combine. And that is your paper.